The other topic is regularization, and this is a rather important topic. So in terms of model, we often talk about complexity, and complexity often represented by the number of parameters. So especially when number of parameters is high or number of parameters is large, we often say the model is more complex. So if your data has more input dimension, you may have more parameter W, the parameter W. And given this, if you don't have enough of data sample, this should be capital N. If you have a low sample size, then your observation may be not enough to saturate W. Saturate. So basically, you don't have enough of data to fit the model. Well, if a situation is like this, where we call that kind of phenomena as overfitting. So the model tries to fit the training data, but the training data itself is not representing the population enough. So data set is small, that means your data set is not enough to represent your population. So that is referred to as overfitting. So your model is not representing as a result the population. And this will be even more serious if you use the basis function or feature function. Since if you look at the previous case, where original input is one dimension, and you increase the number of parameters from 1 to 3. So where you increase the number of parameters somehow, and if you have not enough data, well, your chance of overfitting is increasing. Well, anyhow, well, we are talking about model complexity in terms of parameter. And maybe you don't have enough of data to fit well, that much of a parameter. So one solution is to simplify the model. In other words, well, maybe you can shut off some of those W value. So indeed, the slide is suggesting three different options. One is feature selection or surface selection. So we are going to talk about it later in the semester. The method that I mentioned as shutting off some of the parameter that is referred to as ridge regression or lasso regression, or in general, regularization. So let's take a look at the idea. So regularization is again shutting off some of the W. So earlier we said we have too many variables or too many parameters. So maybe we can simply rule out some of the parameter value. So say W1 is indeed 0, and we fix it. Then we have less number of parameters, and we simplify the model. So this is the idea. And then the next question is how to select which W to shut off. So one of such option is ridge regression. So ridge regression is adding one additional term that is lambda W square. So this is a scale of L2 norm and defined as this. So you simply scale each individual W and take the summation of it. And that is called as scale of L2 norm or L2 penalty term. So what you are doing here is simply adding that at the end of your error function. So idea is where we want to minimize this error. And we add it, well, this as a constraint. So each time we want to reduce down this error, but at the same time, we want to make W smaller. So this is the idea. And here lambda is deciding the effect of the penalty. So the idea is simple. So you simply add this L2 penalty at the end of your error function. And again, you take the derivative of it and set it to 0. Thankfully, the derivation of this updated error function is really not complicated. So, well, this second slide is showing how this changes the linear regression in terms of a system of linear equation, where we were trying to solve this function. Adding this L2 penalty, it eventually changes the above function in this way. So that was the idea of L2 regularization or Ricci regression or Ricci regularization. Everything is okay. So this is one idea, and let's quickly move to the other one, and let's try to understand and comparison, things like that. So the other option is lasso. So lasso regression is, well, looks like almost the same. Only difference is this term. So previously, which was adding this square term. Now we have, well, this different one that is L1 penalty. So it is taking the sum of all the absolute value of W. And again, this is the regularization coefficient. So this is deciding the effect of the penalty term. So if lambda is large, your model is going to get simpler. And lambda is small, model is getting more complicated. So we have two options. One is Ricci, the other is lasso. So Ricci is taking the square of W, and lasso is taking the absolute value of W. And its practical meaning, it's sort of adjusting your W value in this way. So
this is representing the values of the regularization term for different values of W. So for some of the unimportant input variables, maybe your W becomes close to 0. That corresponds to this area.
while your W is sort of small, this Ricci regression is suppressing your W value this much. So compared to this orange line, which represents L1, the penalty quantity is smaller, right? Again, this orange line L1, blue line L2. But if your X, your input variable is not really important, your W is also smaller, corresponding W is also smaller. Within that area, so say your W value is around 0, L2 is smaller, L1. That means L2 is sort of mild in terms of regularizing the model. L1 is sort of more strict in terms of regularizing the model. So practical meaning of it, if you use L2, unnecessary parameter values, they are going to close to 0, but not exactly 0. If you use L1, you may have on this. If you use L1, you may have some unnecessary W, and they will become exactly 0. So these are sort of practical difference. And this is one last comparison between Ricci and Lasso, or L2 and L1. So, well, this form was actually familiar to us. So this is defining, well, one of the technique that we studied, Lagrangian multiplication. So we initially have a goal. This is the objective, and we have constraint, and we combine the constraint and objective with lambda. So this is the Lagrangian. And again, L1 is the same. So constraint over there, and that is combined with lambda. And our goal is to find W and lambda at the same time. And well, this is my bad. Actually, this is lasso. Well, I don't know why I put lasso on this side. This is lasso, and this is Ricci. So the constraint space The constraint space is highlighted with sky blue. So each is L2 penalty that is defining a circle like this. And lasso is defining some square in the space like this. And well, while we are optimizing this Lagrangian multiplier, we are eventually finding where the contour of W is meeting with this constraint area. But lasso, well, if you think about reach, well, things are circular. So the distance from W to any of these points, well, they couldn't meet anywhere in the middle. But lasso, things are angular like this. So the chance of meeting this contour with your constraint space, maybe you're meeting things at one of those axes. So this diagram is showing that. So again, this is lasso, this is reach. The constraint space of reach is a circle. So well, if you expand the contour of W, well, maybe it will meet anywhere on this curvature, but things are straight here. So if you expand your contour, it may meet one of the points on the axis. So well, this is illustrating why L1 is promoting large of 0 in terms of parameter, and L2 instead so large of a small parameter. And well, this is something called the regularization plot. So if you look at the change of W value while you're increasing the lambda, well, maybe some of the less important parameter that will shut up first.
So among these multiple weight parameters, this guy is maybe the most important one, and less important, less important, less important, and so on. Something like that.
Anyhow, but while you are increasing the lambda value, maybe some of the parameter value will get smaller or will get to 0. And well, those parameter value who get to 0 earlier, that means well, the variable is less important. So well, this is the end of linear regression. So make sure you understand most of the important topic, and at the same time, if you have any question, let me know.